Hello everyone. This is a talk that I gave to the Heterogeneous Computing Workshop at IBDPS 2023 this past May, which focuses on work by my team to be able to develop applications which use more than one computing resource effectively. Now, this work is built under the context of the increasing complexity of ways that artificial intelligence is used inside of scientific applications. As well illustrated by Shantanu Jha and colleagues, there are many different places inside of an application that a workflow might need to be used, an AI tool might need to be used. And given the prevalence of the different hardware environments that are available for executing these AI workloads, it's becoming increasingly necessary to have a single computing application that coherently spans more than one type of computing resource. And that's what we've been studying closely over the past couple years on how to create software that enables these complex applications and makes them high performance. And the challenges come into play here because the ideal location for a heterogeneous resource is rarely the one that we find in practice. Ideally, you want all of your computing resources to be part of the same site, to share perhaps a file system or a job scheduler, such that a single workflow engine can connect to the file system and exchange data, talk to the scheduler, all without having to interface with those difficulties that arise at the boundary between computing systems. What we find more often is that each of these computing resources we want are on separate facilities, each using different authentication mechanisms, different schedulers, residing on different file systems. So building these kind of applications necessitates solving challenges around data movement, security, co-scheduling, all of which contribute to make building these kind of applications a relatively rare occurrence. That's not to say that it isn't something that people do. There's in fact some great work from colleagues at Argonne illustrating how to use two coordinating supercomputers to solve the same challenge in biology. Such examples do exist, but we want to make them easier and particularly make it easy to get good performance out of those applications. So with that said, what this talk is going to focus on and what our paper that I'll link in the description of this video studies is how we can build these kind of applications using two different examples which illustrate different types of coordination patterns. Both are in this machine learning out of the loop or about the loop type applications as categorized by Shantanu, but they differ in the amounts of data and the amounts of compute of simulation versus AI that happen. So they illustrate two different challenges in optimizing the performance. So what we're going to study over the course of this talk is how we've constructed a solution to make building these kind of applications relatively secure and fast compared to baseline ways of approaching these applications, and in a way that minimizes the amount of, say, networking or security burden that occurs. So what we're going to do is we're going to go through the two applications I've alluded to in a little more detail so you understand what we're trying to solve, explain how we solved it, and then go through the results illustrating that our proposed solution works at least in these two cases. So as I mentioned, the first thing I want to do is talk about the applications themselves. What we started with is the hardware. We want to tie two different computing resources together. The first of which is the venerable Theta supercomputer at Argonne, which is around 4,000 CPU nodes, scheduled using a bespoke scheduler that was created at Argonne called Cobalt. This we used to perform our simulation tasks. For the AI, we used a NVIDIA DGX box, which is called Venti. It's also available at Argonne, but houses a very different kind of hardware, 20 of NVIDIA's T4 series GPUs. It's a free-for-all system, so there's no scheduler, but it's not one of our newer boxes, so we're able to use it exclusively for many of our experiments. And I will note both of these computers are at Argonne, They use different security systems, different schedulers. They don't share a file system. So this gave us a way of emulating a multi-site application where all of those sites happen to be housed in the same data center and were available to us using the same computing account or through similar computing accounts. So the first problem that we studied was a molecular design application, which was one that we built using Colmena in some of our previous papers, and it follows a fairly well-described type of design problem as illustrated well by one of my colleagues' 2020 papers. This sort of application uses three different tasks. The first of which is simulation. I take a single molecule and I compute a property, namely the ionization potential, which I want to maximize. I then have training tasks which take that molecule ionization potential mapping and train a message passing neural network. In fact, we train an ensemble of 8 of them. And then we run inference tasks where I take a space of around 10 million molecules, I evaluate all of them, and then I find the ones that have the largest upper confidence bound, the largest sum of the mean prediction of those 8 models with the variance. And that's a fairly common active learning strategy. This application, when we implemented it using a baseline tool, just a standard workflow engine, suffers problems of underutilization of the GPU nodes and CPU due to the large amounts of data being transferred. What happens here, and what I'll show you later, is the workflow engine is bogging down because it's blocking while sending large data objects between the two systems. So we're going to show you how to eliminate that problem later. The next application we studied is a newer one for us, where the goal is to fit a surrogate function for costly computational methods, namely creating what's known as an interatomic force field for density functional theory calculations of water clusters. What this application does is runs 4 different types of tasks, the first of which is a simulation task. Takes about a minute or between 1 and 10 minutes each, where we perform the simulation we're trying to build an emulator for. The second type of task trains a machine learning model to emulate that simulation. We also train an ensemble of 8. The next part is where we have a different workflow than our simulation component, our previous active learning example. We perform sampling tasks where I take that surrogate model and I perform a molecular dynamics simulation to generate new potential structures. I use inference to identify which ones of those are going to be best to simulate. I simulate them, retrain the model, and that allows me to create a cohesive application which can train a very good surrogate. And the advantage, as illustrated in this plot on the right, is that all 4 of these types of tasks can occur concurrently on our 2 different resources. And this one has a much different compute to data ratio. Instead of 100 gigabytes over 2 hours, we only send a little over 1. And that's owing to the relatively small size of our inference and training spaces compared to the compared to the molecular design example. So those are our 2 problems, both implemented using Colmena to orchestrate 3 or 4 different types of simulation and learning tasks, both with very different compute to data intensities. So given these 2 applications, we wanted to create a single approach that could make the application performant on both systems or current together. Now, building these on top of Colmena, we have an architecture that has 4 different types of services running together. The first of which is a thinker application, which orchestrates which kinds of tasks are being run. It delegates them to be computed by sending requests to a task server. The task server is responsible for sending data across to an endpoint running on a remote system that communicates with workers that are on the actual compute nodes. So there are 2 main parts of the communication between sites which occur here, I'll emphasize. The first of which is a task description that gets sent along to the compute resource. And we also go through the process of decoupling that task orchestration command from the data which is being consumed or produced by the task. And that occurs via the second channel, which we call a value store. So given this architecture, we wanted to achieve a few things besides performance. The first of which is we wanted to do this in a way that is completely adherent to the security policies of our computing resources, which are strong. The second of which is performance, of course. We want this to work very well, and we want to ensure that it can scale up to large supercomputers. We also want to do this in a way that minimizes the amount of human effort in setting up and maintaining that system. We want it to be robust, and we want to be able to achieve that same degree of robustness on different computing resources. So given that, we came up with a few different collection of tools that allow us to create a multi-site application that's efficient. The first of which I'm not going to go into much detail about. It's Colmena. That's the tool that we use to express our workflow. But what we've explored in greater detail are the tools which execute work across multiple sites. I may call the tool FuncX. It's recently, as in the past 2 months, been rebranded as Globus Compute, as the Globus platform adopted the FuncX technology to provide distributed computation along with their data transfer services. We use Globus Transfer to send data between multiple sites, and we make that robust and simple to implement using a tool called Proxy Store. So let's start with the compute part. Well, we use Colmena, as I mentioned, to express our training policy. It enables us to create complex applications that can hide the latency inherent to sending data across multiple systems, and it allows us to decouple the steering logic from the execution, so it's portable. The execution environment we chose is based on Globus. It's secure, being built on top of the authentication technologies that Globus has created to secure data transfers between multiple centers. It uses industry standard tools. You can use multi-factor authentication with it if needed, and it integrates cleanly with the account management systems at different computing sites so that you can use Globus with many different securities using the security policies available on those sites. The back-end performance, we call it in the paper FuncX, it's now called Globus Compute, is robust because it's managed by a cloud-hosted services. Once you delegate your task to Globus Compute, Globus's web services are managed by somebody else. So keeping your task alive over, say, disconnect from your workers or your steering process is managed by the cloud-hosted service, not you. It's also high performance. You can manage 10,000 workers with Globus Compute, and it's portable. You can run Globus Compute on any computing system, and importantly, you can do that without setting up any specific networking to that compute site. The way that Globus Compute works is that it connects with an outbound connection from that computing site to the cloud services, which, so long that it's approved by your computing site, doesn't require any additional networking effort on your behalf. Globus Transfer is very similar. When you request data to be computed, a cloud service makes it happen. It's built on underlying technology that can achieve very fast data transports, and it's portable. Most computing sites that you use probably already have Globus installed if you're going through the DOE or the US National Science Foundation's Access Program. So this is a solution that we know we can use across many different types of computing ends. The last bit that we did for performance's sake is to decouple the data transfer aspects of our requirement from the compute messages, especially when we're using a cloud-hosted service like Globus Compute to transfer control messages about which tasks to run through a cloud. We don't want to send large task messages through that third-party cloud service, both because one, Globus Compute limits those transfer messages to only, I think, 10 megabytes in order to, prevent bottlenecks in the cloud and large egress charges for running that service. And secondly, even if Globus Compute allowed it, we wouldn't want to do that because data transfer between two legs up to the cloud and down is probably going to be slower than directly transferring between peers. So what a direct pass by reference solution that we implemented allows us to, one, speed up that transfer. Additionally, it speeds up whichever workflow engine, be it FunkX or something else, by not sending large messages through control channels designed for high latency. And because we've broken off our data transfer into its own subsystem, we can optimize that subsystem for particular network setups completely separately from developing the compute architecture. And we do that using a tool called Proxy Store. Proxy Store is its own thing. We have a paper for it that I believe was recently accepted to SC 2023. So the paper's up online. I'll link to it in the description. But for the purposes of this talk here, what Proxy Store provides us is an ability to define a multi-site data fabric, like we can use perhaps Redis if open ports are available. And given that data fabric, you can pass an object in Python to it. It creates you a reference that acts as a proxy to it that you can use in any function. As soon as that object is used, the data fabric will access the data for it, dereference your object, and allow it to act just like a normal Python object, the one you originally created. In Colmena, you can do this either automatically by ensuring that any data object passed to your task server over a certain size is placed in that data fabric, or you can do so manually. And this manual process is one that we use to further optimize data performance. For example, if I know I'm going to use the same training set across all tasks, I'll create that training set once. I'll send it in advance of me sending copies of the model. Or I could say cache my search space ahead of time. So in short, what this allows us to do is create high performance data transfer without much change in our application, and we can use many different data fabrics. Globus will be the one that we'll use in our multi-site implementation, but depending on your network, you might be able to use something like Redis. All right, so that defines our applications. Let's go through talking about how well they performed. And we're going to do that using three different tools. We're first going to explore it through a very simplified application so we can understand what these different overheads in our application should be. I'll then show you those two different applications, I'll show you one of those two applications in a deep dive to illustrate that we're actually achieving the overheads we expect in practice. Then I'll show you both applications and illustrate that we get the same performance with our simplified multi-site tool as we do with an application that was highly optimized but required a lot of setup to achieve that multi-site performance. So in the first case, we wanted to dig in to what are the penalties that we should expect for building a multi-site data fabric. Now, the first thing we started with is comparing how different a multi-site data transfer is compared to a single site. Oh, pardon my alarm going off. In this particular case, we had a single application where I set up my compute all on the same site. In one case, for my single site application, I tested two different data fabrics, one where all data is passed in memory via Redis, another where they're passed via the file system, so that I can compare to a multi-site implementation where my steering mechanism is on one site and the workers consuming the data produced by the steering tool are on another. And what you can see here is a comparison of different forms of latency as a function of task size. And you can see that for our single site application, our task takes about a second of overhead for the data transfer. And that's looking at, and that's basically invariant to the task size. With Redis at very small task sizes, it's basically free to put the data in a Redis service and transfer it out later, but that becomes increasingly more costly as the size of the data arrives, such that at a dataset size of about 100 megabytes, it's about the same as writing the file to disk anyway, even though we achieve or find a larger cost just to create a file. We see about a 3-second transfer of data for Globus. As you're going to see highlighted in further and later parts of the talk, most of that time is the result of both communicating with a web service, about 100 milliseconds, and for the transfer to be started up, which is about 2 to 3 with Globus. So we're going to find that really regardless of the amount of data you're transferring, we're going to incur about a 3-second penalty for transferring that data to another site. And that's kind of invariant to the size of the data for this particular application, because our data sizes are small enough that our data transfer cost is small. Once Globus starts going, it's very quick. So in short, Redis works great for small objects. If we're both on the same system and our data set sizes are smaller than 100 megabytes, then the file system is also equally good. Globus latency, it's created by trying to read the file, which that time is in waiting for the data to show up. So looking at whether we actually achieve these data in a real-world performance, let's go and dig into that molecular design application that I talked about in greater detail. So here we have 3 forms of latency that are problematic. The first of which is a task completing on that remote system and the amount of time it takes for the thinker to be notified of its completion. The second time is how long does that thinker take to produce the next task to be run. And there's a third form of latency that is dispatching that task onto the remote worker. And we're going to look at each of them separately. So in our first case, the reaction time, we actually broke into 2 segments. The first of which is the amount of notification. So here the notification time requires just the task completing, a proxy for the result data being created, and then the result message and that reference, the proxy, to the data being passed to the steering process. In our particular example, we have 2 different systems being used. For simulation, we use a system that is on the same site of our storing pattern. So creating a proxy is very quick. All we do is write the data to disk and then pass the reference. So our latency for transferring is only about 100 milliseconds. That's the latency of sending a task control message through Globus. Accessing the data is also about 100 milliseconds. It's about 300 milliseconds on average. And that's the amount of time it takes to read the data off the disk. So very quick, less than a second for simulation for this reaction time. The AI is a bit longer. Notifying takes about 1 second. Most of that time is spent creating the reference. Here, because it's on an opposite or a remote site from our steering system, we have to first write the data to disk and then register that data to be transferred with Globus. That takes anywhere between 100 seconds or 100 milliseconds to 1.5 seconds. And actually accessing that data, and according to that earlier benchmark I showed you, takes about 2 to 3 seconds. We called it less than 10 to be on the pessimistic side. So it can take about or a bearable amount of time. It's still under, say, 99% of it's under 1% of our task execution time. And our training takes about 8 minutes, so 4 seconds isn't very large, but it's still something that we have to design around. The decision time is something that's relatively boring. There are two parts where the decision time actually plays a role. The first of which is selecting the next molecule to run. That takes 5 milliseconds of just popping the next molecule off the queue and submitting it. So that's small compared to my data transfer costs. It's less than like 1 part in 1,000. The time where decisions are expensive is reordering the task queue. That takes 4 seconds, most of which is actually a result of the data transfer. So it's more of that reaction time latency, but here we have a hard time measuring it separately from the decision process. So this is 4 seconds. It's all data transfer. Not particularly interesting. The dispatch times are also not particularly worth further study. The startup for our training task takes about 4 seconds. That's the data transfer time. Inference tasks, there's one where the dispatch is costly. It takes about 3 seconds. Also transferring the data and the model back to the remote system. So that's another one that is noticeable. We can measure this time effectively, and I know where it's coming from, but it's just small compared to the overall time spent on inference. Same story with simulation. It takes on average about 100 milliseconds. That's for a task to get started up. The inputs are very small, so we don't have to proxy them, but it still takes 100 milliseconds for the control message to go up to Globus Compute, back down to our remote endpoint, and get shipped out to the worker. But given that these tasks are on the order of a few minutes, this results in a 99% CPU utilization. So while there are possibilities for optimizing this, perhaps, one, it's very small, and two, we could hide this latency by submitting more tasks to the simulation workers than we actually have execution slots available, so that this latency of 100 seconds is hidden. So here we've shown in a deep dive that we're getting those overhead numbers that we expected from our synthetic applications. They're small for our particular application of molecular design, but we want to study this in greater detail. Do we actually get the same scientific performance with these overheads? In the story here, we wanted to study not just are we getting good scientific performance, but does it compare well to a baseline? So the first baseline we did is just a simple workflow engine, no effort on multi-site data transfer. The other, we created this workflow engine where we also used our best performing data fabric, Redis, and we opened ports on both of our compute systems using an SSH tunnel such that we could do this without having to resort to cloud services to enable that multi-site data transfer. And we compared both of these with our proposed cloud-hosted solution, which again is Globus Compute, FuncX with Globus Transfer. And in both cases, we found that the scientific performance is unhindered. What I'm showing you for our molecular design is the number of good molecules we found as a function of compute expended. All three methods are within intra-run variation or inter-run variation of the same task. So here performance is good, and we can show that the performance numbers are similar. In fact, the AI tasks, here I'm looking at the machine learning make span, the time between when I start retraining a model and when all inference tasks have complete is faster with FuncX and Globus, because that solution allowed us to cache data on the remote system ahead of time. So it avoids any of the data transfer costs that plague either of the other solutions. It does have a larger CPU idle time for the simulation tasks. It's a few hundred milliseconds on average, and that's because of that 100-ish millisecond reaction time penalty and the dispatch time. For our fine-tuning surrogate application, we also find that all three are the same within inter-run variation, and we see similar stories. The multi-site application in red is slower than our two baseline implementations because it involves initiating a Globus transfer. Data access takes a few seconds. for each of these tasks. And similarly, our simulation tasks they've got about a few hundred millisecond overhead, partly due to data access. We have to write data to the file system, but mostly due to the control messages having to go through a cloud service first. But I will note, science is the same, and our utilization is still high, above 99% in all of these cases. So that wraps up our talk for today. The one thing I want to emphasize besides the conclusions here is that all of the software that we used is open source and available for free. I took all of our implementations and made them of the applications and made them available on GitHub, along with a published version of not only the results that we needed in this study, or that we created to support all of those conclusions I gave you, but also the inputs needed to recreate those experiments yourselves, and that's published on the Materials Data Facility. So to wrap up, what we've illustrated is a proposed solution for creating multi-site applications where we use cloud-hosted services such as Globus to ensure security, yet also minimize our networking effort to deploy that application. And we build a data fabric on top of Proxy Store in order to ensure that data moves between sites effectively. So this wraps up basically our examples showing that this solution works with two different types of workflow applications. We're still working on more types of multi-site applications, exploring whether our conclusions hold using different architectures and different resources for deploying these applications, and hoping to further bring down some of our performance numbers, especially on those small task size data. And this will be work that you can read about in Greg and Valerie's recent paper on Proxy Store. If you have any questions, feel free to email me. I am back from camping now, but was gone for the 2 weeks after I gave this original presentation. But still, feel free to email me or comment on this video if you have any questions. So thank you for tuning in, and happy to talk about this work more if you'd like to. Have a nice day.